Okay, so we're going to review the notes that we went through with circular motion. And this is just an introduction to circular motion and understanding that when something is traveling within a circle, what's actually happening with the forces and the accelerations and the velocities. So the first thing we talked about was that if ever we try to find speed, that is simply the distance that something travels divided by the time. In a circle, when we're traveling around in a circle, that is the circumference is my distance, and then the time. My circumference is going to be 2 pi r divided by t for my speed, or as well as diameter times pi divided by time. All right, so that's the main way that we're going to get speed. Essentially just distance divided by time, but understanding that my distance is my circumference of the circle. Okay, now what we talked about is that when something is in circular motion, it is accelerating. And that's because these velocities, velocity 1, 2, 3, 4, right? The velocity is changing, and that's because the direction is constantly changing. So while this is traveling around a circle at a constant speed, the velocity is constantly changing, which means that we are accelerating. And this velocity is considered a tangent velocity because it's always tangent to the circle of motion. Okay, now we said acceleration is a change in velocity divided by time, which in this case would be velocity 2 minus velocity 1 divided by time. So in terms of vectors, right, velocity 2 points to the left, velocity 1 points upwards. And so if we do 2 minus 1, that's the same thing as doing velocity 2 plus a negative velocity 1. So if we add these two together with a negative velocity 1, it's going to be velocity 2 plus a negative velocity 1. And so this would be the direction of my change in velocity. Okay. Now, when we add that to this circle, that means for this red portion of my circle, my change in velocity is towards the center. If I do the same thing with velocity 2 and velocity 3, they're also going to add up to a change in velocity here. If I do velocity 4 minus velocity 3, it's going to point in this direction, and then velocity 4 minus velocity 1, or 1 minus 4, excuse me, is going to be pointing in this direction. So we see that for all 4 phases of this motion, the change in velocity is always towards the center. And the change in velocity is the same as my acceleration. So we're going to say that the acceleration of an object when it's in a circle is always pointed towards the center. And most people would say, well, that doesn't make sense. It feels like I'm getting pushed outwards, right? But remember, anytime we're actually accelerating, our body feels like we're actually getting moved in the opposite direction of our acceleration. Okay, so we just had a quick conversation of if I'm sitting in a car and the car all of a sudden has an initial velocity of 0 and then all of a sudden it starts moving, I feel sitting in the car, I feel like I'm getting pushed this way, but my acceleration is forward. And this sensation of getting pushed back is simply the idea that you have inertia, and so your body wants to keep doing what it's already doing, right? When an object is turning, if we're in the car and we're turning, right? So let's say we're in the car and we're going straight this way, and then the car starts moving this way. If I'm sitting here, I want to keep going straight. And so as the car bends, right, I have come in contact with the outside of the car, right? And so it feels, and I have this sensation that I got pushed outwards. But instead, it's just my body desiring to go in a straight line and the car moving. And then the car is actually going to be pushing towards the center of my circle, okay? And so I'm going to be accelerating in that same direction towards the center, even though it feels like my body is getting pushed out. Okay, and we tried to support this idea that the force and the acceleration is actually inward by using the flying pigs. Okay, so we had a pig that was just stationary, and when that's true, if it's hanging from the ceiling, we had the gravitational force down and we had the tension force up. And we said that the sum of the forces in the y direction was tension minus force of gravity, and those equal 0, right? Because Newton's first law says that an object with a net force of 0 is going to stay stationary or have an acceleration of 0. Right? Now, when we had this pig actually moving and we moved it within some circle, okay, it doesn't matter if it's clockwise or counterclockwise, we still only had two forces. We had tension and we had gravity. But tension now was at an angle. So we had to break tension into its x and y components. Same thing here, x and y components. The y components still have to cancel out. This is not accelerating up or down, and so tension in the y minus the force of gravity equals 0. So this y component and the gravitational force are equal in size. In my x direction, though, it's only the tension in the x. There is no other force balancing that out, and so I am actually have a net force, which is inward in this case, towards the center of my circle. If it's over here, doesn't matter which way I'm swinging, my tension force is this way, inward, towards the center of my circle. So we see that if there is a force pointed inward on a circle, it can cause me to accelerate, which is AC, that is centripetal acceleration, or a center-seeking acceleration. So we talked then the idea that doesn't matter any position on this circle, this is the picture I'm going to have, where I have a tangential velocity, an acceleration towards the center, and a force towards the center. And that's going to produce circular motion. Whenever my force is perpendicular to my velocity, it is not causing me to speed up or slow down. It is simply causing me to change directions, right? So for 2, my force would be, or my velocity would be here, my acceleration would be here, and my force would be there. At this position, velocity, acceleration, force, velocity, acceleration, force. Okay, so force, acceleration always point towards the center. My velocity is always tangent to my position, and my velocity and my force, or my velocity and my acceleration, are always perpendicular. Okay, and so some things that we said was that when something is accelerating in a circle, we can solve for that acceleration using the equation vt squared over r. So if I know the tangential velocity, and I square that divided by r, that's going to give me my acceleration. I then said that Fc equals mac, so this is just F equals ma. And so if it's centripetal force, it's a centripetal acceleration, and I can then rewrite this as mvt squared over r. And we made a note, and we'll do some practice with this, that Fc is not its own force, but instead it's the net force when the net force is perpendicular to the velocity, okay? And we simply said that you will never, this is a no, you will never see it written as, the sum of the forces equals force of gravity plus Fc minus tension equals mac. Okay, that's not how it's written. This is the mistake. Fc is never its individual force. It's not its own force, but instead it's the net force that results when the net force is perpendicular to the velocity. And so an example that we'll give is, if we're going over top of a hill, okay, you have two forces acting on you. You have the force of gravity and you have the normal force. Okay, now in this case, my force of gravity is actually larger than my normal force, and that's because I am traveling in circular motion, right? My velocity at this case is there, and so if I'm following this path here, that's circular motion. So my net force must be downwards. Let me write it like this. F net must be downwards. And that's going to mean that it's a centripetal force. So we would write it as the sum of the forces in the y direction equals the normal force minus the force of gravity equals mass times acceleration centripetal, right? So this force y really is what becomes the centripetal force there, okay? And we know that centripetal force must always be pointing towards the center of our circle. So then we know that the gravitational force must be bigger than the normal force. And that's how I would set that up, okay? And then I could have, Fn minus Fg equals mv squared over r. So Fn minus mg equals mv squared over r. So that's just how I could set that up, regardless of what the numbers are, right? But just showing us that it's a centripetal force when there is a net force that is perpendicular to my velocity. Because my net force is down and my velocity is to the right, that makes this net force a centripetal force, which I can then say that's MAC instead of just MA. All right, so we'll do some more examples of this, but this is just a good quick introduction to just the simple concepts of circular motion.